Hey there, AP Chemistry. This is Miss Ruark. This is not a podcast. It's just a practice one. So let's jump right in. Okay, here, by the way, are the answers to all of these questions. So if you'd like to pause it right now and check your work, and then you can keep watching if it's not right, and if it is all right, then yay, good for you. All right, so let's keep going. Question number 1 says solid lithium hydroxide is used in space vehicles to remove exhaled carbon. Or carbon dioxide from the living environment by forming solid lithium carbonate in liquid water. Okay, so before we can do anything else, we need to have a reaction. So we have to have lithium hydroxide. Li has a positive 1 charge and hydroxide has a negative 1, so those cancel. And it removes, so it will react with carbon dioxide, and it's going to form lithium carbonate, Li2CO3, because lithium has a positive 1 and carbonate has a negative 2. And then we also have water. Right, and then you need to go on ahead and balance your equation. So if we look through this, we see that it's going to be a 2 here to cancel out our lithiums, and I think we're good. All right, we know that we're starting with 1 kilogram of lithium hydroxide, and this 1 kilogram is the same thing as 1,000 grams of lithium hydroxide. Okay, so 1,000 grams of lithium hydroxide. We need to change that into moles first. So we'll take that, multiply, or figure out the formula mass of lithium hydroxide, so 6.94 plus 16 plus 1.01. And the formula mass is 23.95, so we're going to divide by 23.95. Now, if you're not sure, lithium hydroxide, all right, and then we multiply. This unit has to go on the bottom, so it'll cancel. Okay, mole goes on top. We're looking for moles, and then we put the 23.95 on the bottom. Okay. All right, so 1,000 divided by that gives us 41.75 moles. Okay, so that's what our initial condition is going to be when we start. We're looking for carbon dioxide, so that's what we're looking for. We really don't know what's going to completely, we don't know how much is going to be reacting, and so that's what we're looking for. Our change here is a negative 2x and a negative x, and we're assuming that we're going to 0 for both of those, so we're going to completion. Okay, so we solve for x. So 1.75 minus 2x is equal to 0. Solve for the x. X would be equal to 20.88 moles. Okay, so that number gets plugged in here. We multiply that by 1, and we end up with 20.88 moles of carbon dioxide that's needed to react, or that will react with the 1,000 grams of lithium hydroxide. Okay, so then we're not done, though, because they don't want moles, although it just says how much. Oh, no, it says what mass. So we've got to look for mass. And it doesn't matter if we go to grams or kilograms, your choice. Okay, so I would say just go ahead and go to grams. So we multiply by moles on bottom, grams on top, and we do the formula mass, which is 44.01 grams, and 1 mole of carbon dioxide on bottom. And then 20.88 times 44.01 gives us 918.9288 grams. But if we look here, we want significant figures, 3. So the 9 makes the 8 round up, so it becomes 919 grams of carbon dioxide. So that's how many grams of carbon dioxide you can get rid of when you use 1 kilogram of lithium hydroxide. That's not bad, I guess. All right. Question number 2 says, ammonia is produced from the following reaction. They give us the reaction. The only thing we have to do is make sure that we balance it. So let's go ahead and balance it. If we put a 2 here, that balances our nitrogens, but it gives us 6 hydrogens, so we put a 3 here. Okay, so we now have our balanced equation. N2 plus 3H2, arrow 2NH3. Okay, and the question says, what mass of ammonia can be produced from a mixture of 1 gram of nitrogen, or 100 grams of nitrogen and 500 grams of hydrogen? And so it's a limiting reactant problem. So we're starting with 100 grams of this, and we're starting with 500 grams of this. Okay, so the first thing we need to do is change from grams to moles. So if you want to set up your conversion, go right on ahead. I'm going to say, well, I know I'm going to divide by the mass of 2 nitrogens. So I'm going to divide 100 by 28.02. And I end up with 3.569, or roughly about there. Right? And then I'm going to take 500 and I'm going to divide that by the mass of 2 hydrogens, which would be 2.02, and it'll give me 247.52. Okay? And I know I start with no products. So then what's the change that happens? Well, the change is going to be a negative x and a negative 3x and then a positive 2x. Right? And then we hope to end with 0, and we're going to put both of these to 0 because, well, we really want to figure out which ones are limiting reactants. So we put them both to 0. Right? And then we solve for x. Well, x on this side is going to be equal to 3.569. And on this side, x is going to be equal to 82.51. Okay, well, which one's smaller? Definitely this one. Okay, so this is going to be our x value. So we're going to plug this back in here, and we multiply it by 2. And when we multiply that by 2, we end up with, I'm looking for it, 1.7845 moles. Okay, so that's how many moles of NH3 we can make. But it doesn't ask for moles, it asks for mass. So we've got to change that from moles to grams. So we're going to multiply by 1 mole on the bottom, and then the mass of ammonia, which is 17.04 grams of NH3. Okay, so the moles cancel, we're left with grams, and that gives us 30.40788. But we want 3 and 3 significant figures, so the 0 doesn't make the 4 go up, and it's 30.4 grams of NH3. So that's the answer to the first one. Okay. For the second one, it says how much unreacted material remains. So now we want to look at how much of the excess reactant is left over if we've used this much. Okay, so what I would do here is I would just go on ahead and say, I know that this is my limiting reactant. I know I'm going to use all of this, so I'm going to use this to figure out how much of this would actually react. Okay, so let me set this up again so that you can see it clearly. Okay, I know that I'm going to use 3.569 grams here. I don't know how much I'm going to use here, but that's what I want to know. Okay, my change is still going to be negative x and negative 3x, and I'm hoping that I end up with 0 here because I'm going to use all of both of them. Okay, so just solve for x, which x is going to be equal to 3.569, and if we plug this in here and we multiply that by 3, we get 10.707. Okay, but remember, that's moles of H2, and we don't want moles of H2, we want grams of H2. Okay, so we're going to multiply that by 2.02, which is going to give us 21.628 grams of H2. Okay, so we're saying that if we use this many moles of N2, we will use 21.628 grams of H2. Okay, but the problem doesn't ask for how much we used, it asks for how much is left over. So if we use that much, but we actually started with 500 grams, well, can I take the 500 grams and subtract the 21.628 grams from it? Okay, and so when I subtract those, I'm left with 478.372 grams, which significant figure rules least number of decimal places, and so it would be 478 grams of H2 left over or unreacted. Okay, these are questions that they love to ask, so make sure that you're paying attention. If it asks for how much remains, you have to figure out how much of your excess reagent you used and then subtract that from the amount that you started with. All right, we'll do more practice tomorrow. All right, here's another one. Aluminum burns in bromine, producing aluminum bromide. All right, so it looks like we need another equation. So let's write out equation. Aluminum is going to be Al, and it's going to burn in bromine, so Br2 because it's part of Brinkelhoff, and that's going to produce aluminum bromide. Okay, so we need to balance this. If I've got 2 bromines and 3 here, common number would be 6. So if I put those there, that gives me 6 and 6, but I've got 2 here, so I put a 2. All right, and they want to know if 6 grams of aluminum reacts with excess bromine, and they said, guess what? We're going to make 50.3 grams of aluminum bromide. So they want to know our actual yield, our theoretical yield, and our percent yield. But we already have this one because it tells us that that much is made. So we know that 50.3 grams of aluminum bromide is our actual yield. Okay. Well, then the theoretical yield is how much should we make if it was a perfect world, and that's what we calculate the whole time. Okay, so we have to change this from grams to moles. We divide by 26.98. All right, so 6 divided by 26.98 is 0.222 moles. Okay, we don't know how much of this we're starting with. We're just starting with a lot, so we just leave that blank. We know that our initial that we start with on the product side is 0. For change, it's going to be a negative 2x, a negative 3x, and a positive 2x. And then for our ending point, we hope we're ending with 0. We're not going to worry about this one. And we know that we're going to end, well, that's what we want to know. How much will we make? Okay, our theoretical yield, how much should we make? All right, so if we set this equal to 0, solve for x, x would be equal to 0.111. And we take that number and we plug it in here, and we end up with 0.222 moles of AlBr3. Well, we've got to take that number and multiply by the formula mass of AlBr3, which would be 1 mole and 266.68 grams. Okay, so moles cancel, and then when we do the math for that, we end up with 59.20 grams, but we don't want that much. We want, look, 2 significant figures. So the number even that I gave you was incorrect because I gave you 59.2. The answer should be 59 grams. Okay, and then to find the percent yield is actual over theoretical, and then we times it by 100. Okay, so if we plug in the actual yield, which is 50.3, and we plug in the theoretical, which is 59, and then times it by 100. Okay, the calculator is going to give us 84.97 or somewhere around there percent. Okay, so technically 2 significant figures, it should be 85%. And there's your answers. All right, let me see if I can get one more out of here. Okay, years of experience have proven that the percent yield for the following reaction is 74.3. And then letter A, it says that we have, oops, let me get my pen on here. All right, 10 grams of mercury, and then 9 grams of bromine. And it says how much HgBr2 will we make? Now that's what we want to know. Alright, so we've got to go from grams to moles on both of these. So we take 10 and we divide that by the mass of Hg, which is 200 point, I have it written down somewhere. Alright, well anyways, when we do the math, we end up with 0.0499. Okay, and then when we do the math over here, we end up with 0.0563. And we know that we're starting with 0 for our products. The change, let's see if it's balanced. Yep. So the change here is negative x, positive x. And then we're going to set these both equal to 0 because we want to know which one runs out first. So on this one, x is equal to 0.0499. And on this one, x is equal to 0.0563. Okay, this one is smaller, so it's got to be our limiting reactant, which means that mercury runs out first. Okay, so we're going to use this number and plug it in here to solve for x, and we end up with 0.0499 moles, HgBr2. But we don't want moles, we want grams, so we're going to take that number and multiply by the formula mass, which is 360.39. And we end up with 17.98, but we want 3 significant figures, so we round that to 18.0 grams of HgBr2. All right, and I'll finish the rest of this in the next part.